based on some of the great pillars of our understanding of 20th century science. So in the middle, I'll ask you when I get there, because there are two versions of it. There's one that has the difficult, geeky bit, and the other one that's a simpler explanation. So I'll test you against the previous audience and see which one you choose. You better choose the geeky one, though, because it's quite bad. So what I've got, though, is that I wanted to start just by giving a sense of the scale of the problem. So the 20th century and now 21st century cosmology and particle physics together have come together to give us an unprecedented picture of the evolution of the universe. Not the origin of the universe. The question, why is there a universe, is not currently a scientific question. We don't know what happened at the Big Bang. But we do have a tremendously precise model of the evolution of the universe from certainly 1 billion to the second after the Big Bang, because that's where we can do experiments. And actually, from some new data I'm going to show right at the end of the talk, of something called cosmic microwave background radiation, we have an experimental connection with theories that speak of physics that happened 10 to the minus 36 seconds after the Big Bang. So that's I should say actually, there's the wonders of the universe and solar system drinking game on the web, where every time I say million, you have a little drink. Every time I say million, you have another drink. And there's all sorts of complicated rules. But this is the start for the pub later. So that 10 to the minus 36 seconds is a million second after the Big Bang. Remarkable achievement. Just to get this one picture, which I think illustrates the hubristic nature of modern science. So this claim that we can understand how the universe evolved from its earliest moments to the complexities that we see today is best demonstrated by just one famous picture of astronomy. And it's a picture of a piece of sky, which is actually a piece of sky that's this size, where it says XDF there. It's called the Hubble Extreme Deep Field Image. So that's the piece of sky relative to the size of a full moon. The other way of thinking about it is this piece of sky you'd cover if you took a 5-pence piece and held it, let's say, around 20 metres away, 60 feet or something like that. So a 5-pence piece, 20 metres away. And what I'm going to do is I'm going to zoom in. That's the constellation of Orion at the top there, actually. And the piece of sky is somewhere around here. So this is a zoom in to that piece of sky. So over decades, actually, for thousands and thousands of seconds, the Hubble Space Telescope, which is in orbit around the Earth, took a high-resolution, long exposure image of this piece of sky. It was chosen deliberately, because from the surface of the Earth, it's not particularly interesting. So there are no bright stars in there, no tremendously beautiful galaxies that you can see, certainly with ground-based telescopes. So it's a dull, uninteresting, tiny piece of sky. But this is the image, the latest version of the image from Hubble, the Extreme Deep Field Image. And you see, first of all, it's anything but empty, full of structure, full of points of light. And in fact, virtually every point of light in that image is a galaxy. It's not a star. There are probably 2 or 3 stars in this image. You see some of them, these spiral galaxies, irregular galaxies. In fact, there are over 10,000 galaxies that have been identified in this image. Remember, it's 5 feet, 60 feet away piece of sky. The most distant galaxies in this image are over 13 billion light years away, which means that light took 13 billion years, travelling 186,000 miles a second to reach Earth. It was more than halfway to the Hubble telescope before the solar system formed. So some of the most distant structures that we see in the universe, 10,000 galaxies. If you extend that over the entire sky, and you get maps like this. This is a spherical map of the sky with each point of light representing a galaxy with, on average, 100 billion stars, anything up to 1 trillion stars like our sun. And we've recently found, in the last few years, that we now think that most of those, if not all of the stars, to a good approximation, will have solar systems. So you have 100 billion stars, probably 90% of them will have planets around them, and there are 100 billion stars in each one. There's 350 billion points on that map. So we think there are now 350 billion galaxies in the observable universe, about double that in terms of dwarf galaxies. Just to get a sense of scale, that's the 1 billion light year rule there, by the way. So it's like 1 billion years to get across that big of a map. So the universe is big as well. And that's the observable bit. We have strong evidence now, almost certainly the universe extends well beyond that bubble that we can see, may even be infinite. But the bit we can see, which is about 90 billion light years across now, contains 350 billion galaxies. And we've discovered over the 20th century, basically 20th century science, that all that, everything we can see, is made of actually 3 fundamental particles, or 4, if you count something called a neutrino, which are these 4 here. So the most familiar, and that goes for us as well, so everyone in this room, every galaxy, star, and planet we can see in the observable universe, all its light, is made of actually these 4 things. The most common, the most familiar, I suppose, is the electron. So we're made of electrons, and we're made of protons and neutrons, and atomic nuclei, which are made of quarks. So the fundamental building blocks of us, as far as we can see, quarks, 2 of them, the up quarks and the down quarks. You need 2 ups and a down to make a proton, you need 2 downs and an up to make a neutron. So you need, basically, those 3 building blocks to make up us and everything we can see in the sky, held together by 4 forces of nature. Now, I'm not going to mention gravity very much in this talk, not at all, actually, because it's tremendously weak. It's so weak that in particle physics we don't see its effect on the fundamental particles. It's another drinking game on, but it's a million times weaker than the other 3 forces of nature, for a reason that we don't understand. Nobody has an explanation for that, but it means that you don't see its effect on the subatomic scale, and so we have no good theory for how it behaves at the subatomic level. Very good theory of how it behaves on cosmological scales, that's Einstein's theory of general relativity, but it doesn't impact on our experiments as far as we can see in particle physics. It doesn't fit into our theory. But the other 3 forces of nature are here on this thing. They're represented by these things here, these particles which are labelled gauge bosons. Now I'm going to explain, when I explain the Higgs, why they're called gauge bosons. But essentially, look at this one, the photon, for the most familiar one again, the particle of light. And the picture that a particle physicist has is that the force of electromagnetism is carried by photons. So if you imagine an atomic nucleus with an electron going around it, and particle physicists would picture that as being the electron and the nucleus and exchanging photons, so that the protons in the nucleus are interacting with the electron by exchanging these particles called photons, which are carrying the force of electromagnetism. Now I'm going to show in some detail actually later where that comes from. It turns out to be extremely fundamental and extremely important and indeed beautiful. So that's the photon. This one here, the gluon, carries the strong nuclear force, one of the other 4 fundamental forces. That's the force that sticks the quarks together inside the protons and neutrons, and ultimately sticks the protons and neutrons together inside the nucleus. So the gluons are carrying the force that you deal with here, the forces that are at play within the atomic nucleus, fundamentally carried by those things called gluons. And then there are these 2. So the remaining force, these carry the weak nuclear force, called the W and Z bosons. So they are responsible for beta decay. They're also responsible for allowing the sun to shine, which is also where this last particle in this row, the electron neutrino, comes in. So think about what the sun does. It shines by nuclear fusion, and it converts hydrogen into helium through quite a complex process, actually. But the first step of converting hydrogen into helium is to convert protons into neutrons. Essentially, what happens, not quite at first, so what happens in the sun is that you get 2 protons that approach each other. They bind to form a diproton system, so helium-2, if you like, strange version of helium. And then, very occasionally, one of those protons will turn into a neutron. And through the action of the weak nuclear force, then you get deuterium, and that's the first step of fusion in the sun. And in that process, with the force carried by these things, the W particles, a neutrino is produced. Now, the sun burns 600 million tons of hydrogen into helium every second, produces 596 million tons of helium, loses 4 million tons of mass every second, which 3 equals mc squared is the energy, sunshine, and the production of a neutrino. For every time a proton turns into a neutron, we produce a neutrino. That means that at the surface of the Earth, we've measured and calculated, and they both agree, that there are something like 60 billion neutrinos per centimetre squared per second passing through the Earth, so passing through your head. Now, and the reason you don't get a headache is because the weak nuclear force, which is the only way that the neutrinos interact with matter, is weak, or more correctly, and this is the key point in understanding the Higgs particle, more correctly, the weak force is very short range. It's very short range, which means that the neutrino has to come close to one of your electrons or quarks to interact with it, and it's short range.